In this video, we're going to quickly talk about an optional topic we call differentiability. Today we're going to define the term differentiability, and we're going to see what differentiability, or lack thereof, looks like on the graph of a function. So we say that a function is differentiable at x equals a if it is possible to differentiate f of x, to take the derivative of f of x and plug a into the derivative. A function is differentiable at x equals a if f prime of a exists. So for example, let's consider the points at which the function f of x equals cube root of x is not differentiable. If I rewrite this function in the format x to the power 1 over 3, then this becomes f prime equals 1/3 x to the power negative 2/3. And in case this is not really meaningful to you, it may be better to rewrite this in the format 1 over 3 cube root of x squared. The negative pushes the x into the denominator. The numerator of 2 becomes an exponent of 2 on the x, and the denominator of 3 in the exponent becomes the third root. Now, can you think of any locations where this expression might be undefined? Well, having an x in the denominator of a fraction is generally speaking a pretty bad sign, because it means that you might be able to end up dividing by 0. So this is undefined when x is equal to 0. So in the new language, we would say that f of x is not differentiable at x equals 0. It is not possible to find the derivative at x equals 0. To see what is going on here graphically, I've plotted the function x to the power 1 over 3, and let's look in the location where x is 0. Notice that the tangent line at such a location would have to be vertical. But the issue is that vertical lines don't have slopes. So because the tangent line to the equation does not have a slope, and the derivative is the slope of the tangent line, the derivative does not exist at this location. So there are a couple of graphical features that signal that a function is not differentiable. And one of them is when the graph appears to become vertical. Or has a vertical tangent line. As we know, vertical lines have no slope. So a vertical tangent line is a sign that the slope of the tangent line, the derivative, does not exist. There are a couple of other signs that a function is not differentiable at a point. A function is also not differentiable at any location where it's not continuous. So if you're seeing a gap or a break or a hole in the graph, the function is not continuous there, but it's also not differentiable. And finally, the last graphical feature that signals that a function is not differentiable is a corner or a cusp. For an example of a corner, let's consider the function f of x equals absolute value of x. This function looks like a v. So there is a corner located at the vertex where x is 0. And therefore, the absolute value is not differentiable at x equals 0. Graphically, the issue is kind of that at a corner, something like a tangent line really doesn't make sense. No matter how close I zoom in to the location where x is equal to 0, the tangent line and the graph never get any closer. sort of no matter what I do. If I adjust the tangent line even so that it perfectly aligns with the left half of the v, there's still a huge disagreement with the right half of the v. And if I flip it so that the tangent line agrees with the right half, now it no longer agrees with the left half. And this is true no matter how much I zoom in. Let's compare this with a function like x cubed, and its tangent line y equals 0, which by the time we have zoomed in to -5 times 10 to the -6, the tangent line and the function are indistinguishable. So this property was not shared by absolute value. There was no such thing, really, as a line which was tangent to the function at the vertex. So using these principles, we can take a quick look at the graph of a function and immediately identify points where the functions are not differentiable. For example, both of the two functions given here in parts A and parts B are not differentiable at x equals 0. The problem with function in graph number A is that there is a break at x equals 0. So the function's derivative would not be defined there. And the problem with B is that at x equals 0, there's a corner. At a location where the graph is a corner, there's no such thing as a tangent line to the graph at that point. And so in this situation, we would also have an undefined tangent line and an undefined derivative.